Right now, as you watch this, the invisible shield protecting every living thing on this planet is getting weaker. Not slowly, not over millions of years. Right now, in ways scientists did not expect. Earth's magnetic field is changing faster than anything recorded in modern history. The North Magnetic Pole is sprinting away from Canada toward Russia at speeds that forced scientists to update their maps a full year early. A growing hole in our magnetic armor over the South Atlantic has spread to nearly half the size of Europe. And deep inside the Earth, rivers of molten iron that power this whole system just did something nobody can explain. They reversed direction. This is not science fiction. This is not a movie trailer. This is real data from real satellites orbiting above our heads right now, measured by instruments so precise they can detect changes in the magnetic field smaller than the pull of a refrigerator magnet from thousands of kilometers away. And the question that every geophysicist is quietly asking in laboratories and conference rooms around the world is the same one you should be asking too. Is Earth's magnetic field getting ready to flip? Because the last time that happened, 42,000 years ago, it nearly wiped the slate clean. Before we get into what's going wrong, you need to understand what this magnetic field actually is, and why losing it would be one of the worst things that could ever happen to life on Earth. Picture the planet you're standing on right now, about 2,200 kilometers below your feet, past all the rock and all the dirt and all the heat. There's a ball of liquid metal. We're talking about Earth's outer core. It is made mostly of iron and nickel, and it is insanely hot. We're talking temperatures around 5,000 degrees Celsius. That is almost as hot as the surface of the sun. And this liquid metal is not sitting still. It is constantly moving, churning, spinning, flowing in massive rivers and currents deep under the ground. And because iron conducts electricity, and because moving electrical currents create magnetic fields, all of that motion turns Earth's core into something like a giant natural electromagnet. Scientists call this the geodynamo. And the magnetic field it creates does not just sit around the core. It reaches out from the center of the planet and stretches thousands of kilometers into space, forming a massive invisible bubble around Earth called the magnetosphere. Think of the magnetosphere like a force field from a science fiction movie. It wraps around the entire planet and protects everything on the surface from the most dangerous stuff the universe throws at us. The sun, for example, is constantly blasting out a stream of charged particles called the solar wind. These particles are flying through space at over 1 million kilometers per hour. Without the magnetosphere, that solar wind would slowly strip away our atmosphere. It would eat through the ozone layer that blocks ultraviolet radiation. It would expose every living thing on Earth to deadly levels of cosmic radiation from deep space. In short, without Earth's magnetic field, life as we know it probably would not exist. The magnetosphere deflects most of these particles. It catches some of them and traps them in 2 donut-shaped rings around the planet called the Van Allen radiation belts. Named after the scientist James Van Allen, who discovered them in 1958, these belts keep the most dangerous particles locked up thousands of kilometers above the surface, far away from humans and animals and plants. When some of those trapped particles do leak down along the magnetic field lines near the poles, they slam into gas molecules in the upper atmosphere and create the aurora borealis and the aurora australis. The northern and southern lights, those beautiful glowing curtains of green and purple light in the night sky, are actually proof that Earth's magnetic shield is doing its job. So that is what the magnetic field is. An invisible force field powered by a churning ocean of liquid iron at the center of the planet. And it is the single most important thing keeping Earth from turning into a dead, radiation-blasted rock like Mars. Mars is the cautionary tale. Billions of years ago, Mars had its own magnetic field generated by its own molten core. And back then, Mars had rivers. It had lakes. Scientists believe it may have even had a thick atmosphere that could have supported life. But then the core of Mars cooled down. The dynamo stopped. The magnetic field disappeared. And without that invisible shield, the solar wind went to work. Over millions of years, it blasted away the Martian atmosphere molecule by molecule. The water on the surface evaporated into space. The temperature dropped. Today, if you stood on the dusty red surface of Mars without a spacesuit, the radiation alone would kill you. The thin remaining atmosphere offers almost no protection. Every rover NASA has sent to Mars carries radiation sensors, and the readings confirm that the surface receives about 100 times more radiation than the surface of Earth. That is the difference a magnetic field makes. Earth has one. Mars lost its. And the results could not be more different. One planet is covered in oceans and forests and billions of living creatures. The other is a frozen, lifeless desert. Now here is where things start getting strange. Earth's magnetic North Pole, the spot where your compass needle points, is not in the same place it was 100 years ago. It is not even in the same country. For centuries, magnetic North sat somewhere in the Canadian Arctic. It wandered around a little bit, as it always does, but it stayed in roughly the same neighborhood. Then, starting in the 1990s, something changed. The pole started moving faster, a lot faster. Before 1990, the magnetic North Pole was drifting at maybe 15 kilometers per year. That is a slow crawl in geological terms. But by the early 2000s, that speed had jumped to 55 kilometers per year. And at its peak, it was racing toward Siberia at nearly 60 kilometers per year. Over the past 190 years, the magnetic North Pole has traveled more than 2,200 kilometers from the Canadian Arctic toward northern Russia. It has now officially crossed into the Russian hemisphere, and nobody fully understands why it accelerated so fast. Scientists at the National Oceanic and Atmospheric Administration, known as NOAA, and the British Geological Survey update something called the World Magnetic Model every 5 years. This model is what keeps your smartphone compass working. It is what keeps military planes on course. It is what submarines and ships use to navigate the open ocean. The United States Federal Aviation Administration relies on it. NATO relies on it. Every time your phone points north, it is using data from this model. In 2019, something happened that had never happened before. The magnetic North Pole was moving so fast and so unpredictably that scientists had to release an emergency update to the World Magnetic Model a full year ahead of schedule. The pole had already drifted so far from its predicted position that navigation systems were starting to give wrong readings. Airports had to relabel their runways. Military systems had to be recalibrated. The current theory is that two massive blobs of intense magnetic activity deep inside Earth's core are behind the shift. One sits under Canada, one sits under Siberia. For a long time, the Canadian blob was stronger. It pulled the magnetic pole toward itself, keeping it locked in the Arctic. But over the past few decades, the Siberian blob has been growing more intense. The Canadian blob has been weakening. It is like a tug of war inside the planet, and Siberia is winning. According to data from ESA's Swarm satellite mission, the strong magnetic area over Siberia has grown by about the size of Greenland. Meanwhile, the strong area over Canada has shrunk by about the size of India. That is a huge shift in the balance of magnetic power inside our planet. The latest update, released in December 2024, confirmed that the pole is still heading toward Siberia, though its speed has slowed down a bit to about 35 kilometers per year. That sounds like good news. But scientists were quick to point out that even at this slower speed, the pole is still moving faster than it did for most of recorded history. And the biggest deceleration they have ever observed in pole speed happened in just the last 5 years. Something inside Earth's core changed, and nobody knows if it will change again. But the wandering pole is only part of the story. There is something else happening that is, in many ways, far more worrying. Imagine a weak spot in your shield. Not a crack, but a section where the armor is thinner, where less protection gets through. That is exactly what scientists have found over the South Atlantic Ocean, and it has been growing for years. It is called the South Atlantic Anomaly. First spotted by magnetic surveys way back in the 1800s, this is a region where Earth's magnetic field is significantly weaker than everywhere else on the planet. It stretches from the coast of South America across the Atlantic Ocean toward the southern tip of Africa. And it is getting bigger, fast. In October 2025, the European Space Agency published results from its Swarm satellite mission, showing that the South Atlantic anomaly has expanded by an area nearly half the size of continental Europe since 2014. Now, that is just 11 years, and the growth is not even happening evenly. A region of the Atlantic southwest of Africa has been weakening even faster since 2020. Professor Chris Finlay, the lead researcher from the Technical University of Denmark, described the anomaly as not just a single block. He said it is changing differently toward Africa than it is near South America, and that something special is happening in the African region that is causing the field to weaken in a more intense way. The data backs him up. Between 2018 and 2025, the eastern part of the anomaly lost about 600 nanotesla of magnetic field strength. The western part, closer to South America, lost about 200. That is a 3-to-1 difference. And it means the anomaly is not just growing, it is splitting. Scientists now believe there may be 2 separate weak spots forming inside the South Atlantic anomaly, creating a pattern that has never been documented before. Why does this matter? Because the South Atlantic anomaly is already causing real problems right now, not in some distant future. When satellites pass over this region, they fly through a zone where Earth's magnetic armor is at its thinnest. The weaker field lets more charged particles from space stream through. These particles slam into satellite electronics, causing glitches, memory errors, and sometimes permanent damage to circuit boards and sensors. Satellite operators have known about this for decades. They have to program their spacecraft to shut down sensitive instruments and switch to safe mode every time they fly through the anomaly to avoid damage. The Hubble Space Telescope, orbiting about 540 kilometers above Earth, passes through the South Atlantic anomaly multiple times per day. NASA engineers have built specific protocols to protect Hubble's cameras and instruments during each pass. The International Space Station, carrying crews of astronauts, also passes through regularly. The station's walls provide some shielding, but astronauts on board have reported seeing flashes of white light when passing through the region, even with their eyes closed. Those flashes are caused by high-energy cosmic ray particles passing through the walls of the station and striking the astronauts' retinas. The particles are literally shooting through their eyeballs. For commercial satellite companies operating fleets of hundreds or thousands of spacecraft, the anomaly is a constant headache. Every pass through the weak zone slightly degrades electronic components. Over years of operation, this cumulative radiation damage shortens satellite lifespans and increases the chance of unexpected failures. And as the anomaly grows larger and weaker, the area of sky that satellites need to worry about is expanding. It is like a hole in a roof that keeps getting bigger with every rainstorm. So the magnetic North Pole is running away. The South Atlantic anomaly is spreading. But what is actually causing all of this? The answer is 2,200 kilometers below your feet. Earth's outer core is a wild place. It sits between the solid inner core at the very center of the planet and the rocky mantle above it. It is a churning ocean of liquid iron and nickel about 2,200 kilometers thick. The temperatures down there reach 5,000 degrees Celsius. The pressure is over 3 million times the pressure of the air you are breathing right now. You cannot see it. You cannot touch it. You cannot send a probe down there because the heat and pressure would crush and melt anything humans could build. No drill has ever come close. The deepest hole humans have ever dug, the Kola superdeep borehole in Russia, reached only about 12 kilometers. That is not even halfway through the crust, let alone anywhere near the outer core. So everything scientists know about the core comes from indirect measurements. Seismic waves from earthquakes travel through the planet and change speed depending on what type of material they pass through. By studying how these waves bend and bounce, scientists can map the layers inside the Earth the way a doctor uses an ultrasound to see inside a body. Magnetic field readings from satellites provide another window. Computer simulations running on some of the most powerful supercomputers in the world try to recreate the physics of a planet-sized ball of liquid metal spinning and churning for billions of years. And in August 2026, scientists published a finding that stunned the geophysics world. Using data from ESA's swarm satellites and older readings from the CHAMP satellite mission, researchers found that the flow of molten iron in Earth's outer core had actually reversed direction. For decades, scientists studying small changes in the magnetic field had concluded that most of the outer core was flowing mainly westward. But the new data showed that around 2010, something dramatic happened. A large section of the core flow under the Pacific Ocean suddenly switched and started moving eastward. Nobody predicted it. Nobody can fully explain it. On top of that, scientists detected what they call a geomagnetic jerk starting in late 2023 and carrying into 2024. A geomagnetic jerk is an abrupt change in the rate at which the magnetic field is shifting. Think of it like this. If the magnetic field was a car driving down a highway, a geomagnetic jerk would be the car suddenly hitting the brakes or flooring the gas pedal. These jerks have been detected roughly every 10 years since the first one was spotted in Western Europe in 1969. Scientists believe they are caused by rising blobs of liquid metal that form deep in the core about 25 years before their effects are felt at the surface. During the period from 2023 to 2025, there were also multiple severe geomagnetic storms, including an extreme G5 event in May 2024 that was the strongest in over 2 decades. During the October 2024 storm, magnetic observatories in Greenland recorded compass deviations of 16.7 degrees. To put that in perspective, imagine your compass suddenly pointing almost 17 degrees away from where it should be pointing. For a ship crossing the open Atlantic Ocean, a 17-degree error in heading would put you hundreds of kilometers off course. For military aircraft relying on magnetic heading as a backup navigation system, it could mean the difference between landing at the right airfield and landing in a completely different country. For Arctic shipping routes in the far north, where satellite signals can be unreliable and magnetic navigation is sometimes the only option, errors like that could be dangerous. And this is not a one-time event. The 2025 State of the Geomagnetic Field report, published by NOAA's National Centers for Environmental Information, confirmed that the field is shifting, accelerating in key regions, weakening in others, and responding strongly to solar activity. The report noted that geomagnetic storm activity between 2023 and 2025 was some of the most intense recorded during the entire current solar cycle. The picture emerging from all of this data is clear. Something big is happening inside Earth's core. The field is reorganizing, and the speed of that reorganization is faster than anything in the modern record. Now here's the part that keeps some scientists up at night. 42,000 years ago, Earth's magnetic field did something terrifying. It collapsed, not gradually, not gently. The field dropped to just 5 to 6% of its normal strength, and during that collapse, the magnetic poles actually swapped places. North became south, South became north. Scientists call this the Lachamps event, named after lava flows near the village of Lachamps in central France, where the evidence was first discovered in the 1960s. The reversal itself lasted about 800 years, but the transition period leading up to it, when the field was at its weakest, lasted several centuries. For a long time, scientists thought this event was no big deal. Sure, the poles flipped, but life went on, right? Then in 2021, a team of researchers from the University of New South Wales in Australia published a study in the journal Science that changed the entire conversation. They had found an ancient kauri tree in New Zealand, perfectly preserved in waterlogged ground for over 40,000 years. This massive tree, with a trunk more than 2.5 meters across, had been alive during the Lachamps event, and its tree rings contained a detailed chemical record of what happened to Earth's atmosphere during the collapse. By measuring the levels of radioactive carbon in each ring, the team could track exactly when cosmic rays were bombarding the atmosphere. And what they found was staggering. During the weakest phase of the magnetic field, from about 42 Erasmus 200 to 40 Wakar 600 years ago, Earth was essentially unprotected. The ozone layer thinned, ultraviolet radiation surged, electrical storms increased. The aurora, normally visible only near the poles, would have been seen from the equator. The researchers linked this period to the extinction of large animals across Australia and Tasmania. They also noted that this timeline overlaps with the disappearance of the Neanderthals in Europe and a surge in cave art, possibly because early humans were driven into caves for shelter from the increased radiation. The team named this crisis the Adams Event, after the author Douglas Adams, whose famous book noted that the answer to the ultimate question of life, the universe, and everything was 42. And it happened 42,000 years ago, a coincidence, but one the scientists could not resist. Try to picture what the world looked like during the Adams Event. The magnetic field had collapsed to nearly nothing. Without that shield, the solar wind punched straight into the atmosphere. Charged particles that normally get trapped in the Van Allen belts thousands of kilometers above the surface were raining down on the ground. The ozone layer, our second line of defense against ultraviolet radiation, was being eaten away. Skin-burning UV levels would have been dangerously high anywhere outside of shade or shelter. And then there were the auroras. Normally, the northern and southern lights appear only near the poles, where magnetic field lines guide charged particles into the atmosphere. But during the Adams Event, with the field so weak and tangled, auroras would have appeared everywhere. The entire night sky, from the equator to the poles, would have glowed with sheets of color. Red, green, purple, every night, for centuries. It would have been terrifying. Imagine walking outside and seeing the sky on fire above the African savanna or the deserts of Australia. Ancient humans would have had no idea what was happening. The researchers believe that this prolonged period of high radiation, ozone destruction, and climate disruption contributed to the extinction of megafauna across Australia and Tasmania. Giant wombat-like creatures called diprotodons, massive kangaroos, and enormous birds all disappeared during this window. In Europe, the Neanderthals vanished around the same time. The research team does not claim the magnetic field collapse was the only cause, but they argue it was a major factor that tipped already stressed populations over the edge. And the surge in cave art from this period in Europe suggests that early modern humans may have been forced underground to avoid the radiation, spending more time in caves and leaving behind some of the oldest paintings we have ever found. The point is this: when Earth's magnetic field weakened the last time, the consequences were not theoretical. They were real. They changed the course of evolution, and right now the field is weakening again. Now let's talk about something that might surprise you. Humans are not the only ones who depend on the magnetic field. Hundreds of animal species use it every single day to navigate, find food, and survive. Homing pigeons are probably the most famous example. These birds carry tiny crystals of a mineral called magnetite in their upper beaks. Magnetite is the strongest naturally magnetic material on Earth, and the pigeons use it like a built-in compass. Scientists have tested this by strapping small magnets to pigeons' heads, which scrambles their sense of direction. Without accurate magnetic input, the birds get lost. Sea turtles are even more impressive. When a loggerhead sea turtle hatches on a beach and crawls into the ocean for the first time, it is already sensing the magnetic field around it. The tiny hatchling memorizes the unique magnetic signature of that exact beach. Then it swims out into the open ocean and travels thousands of kilometers over the next 25 to 30 years. When it is finally ready to lay its own eggs, it navigates back to the same beach where it was born, using nothing but the magnetic field as a guide. Scientists at the University of North Carolina proved this by placing hatchling turtles inside tanks surrounded by magnetic coils. When they changed the magnetic field to match a location far across the Atlantic, the turtles changed their swimming direction accordingly. The turtles effectively have a built-in GPS system. But instead of using satellites, it runs on Earth's magnetism. Salmon do the same thing. They imprint on the magnetic field of their home river as juveniles. Years later, they use that imprint to navigate back upstream through thousands of kilometers of ocean to spawn in the exact same stretch of water where they were born. Monarch butterflies, which migrate from Canada to central Mexico every fall, use a magnetic compass in combination with the position of the sun. Whales have been found to carry small amounts of magnetite in their skulls, and researchers believe they follow magnetic contour lines along the ocean floor during their migrations. When these magnetic lines run toward shore in unusual ways, it may explain some mass whale strandings. Even lobsters, mole rats, bees, and fruit flies have been shown to respond to magnetic fields. Researchers have found that depriving mammals of exposure to Earth's geomagnetic field actually reduces brain cell growth and affects their ability to think and learn. In one study, amphibians raised in environments with disrupted magnetic fields developed abnormal physical features. The magnetic field is not just a navigation tool. It is woven into the basic biology of life on this planet. And if the magnetic field weakens significantly or shifts rapidly, all of these navigation systems could be thrown into chaos. Migration routes that have worked for millions of years could suddenly lead animals to the wrong places. Sea turtles could swim to beaches that no longer match the magnetic signature they memorized as hatchlings. Salmon could miss their home rivers entirely. Birds could fly off course by hundreds of kilometers during seasonal migration. Whale strandings could increase as the magnetic contour lines they follow along the ocean floor shift and distort. The ripple effects through ecosystems, from the open ocean to the Arctic tundra, would be enormous and almost impossible to predict. If you're finding this valuable, go ahead and hit subscribe. We cover stories like this every week, digging into the science that most people never hear about. Now let's talk about what a weakening magnetic field means for the technology that runs modern civilization. On May 10th, 2024, the strongest geomagnetic storm in over 20 years slammed into Earth. It was classified as a G5 on NOAA's 5-point scale, the highest possible rating. The storm originated from a massive cluster of sunspots called AR3664, one of the largest seen in 2 decades. It produced a series of powerful solar flares and launched at least 7 coronal mass ejections directly toward Earth. When that wall of charged particles hit our magnetosphere, the effects were dramatic. The aurora borealis, normally visible only in places like Alaska, Norway, and northern Canada, appeared over Texas, Florida, and even Mexico. People in Spain, Portugal, and the Canary Islands saw the northern lights for the first time in their lives. In Japan, India, and Hawaii, the sky glowed with colors that most residents had never seen. Satellites recorded the aurora stretching across Montana, Wyoming, the Dakotas, Minnesota, Wisconsin, Iowa, and Michigan from orbit. But the beauty came with chaos. The storm triggered what researchers at MIT called the largest mass migration of satellites in history. Thousands of spacecraft in low Earth orbit had to fire their thrusters simultaneously to maintain their altitude as the upper atmosphere swelled and thickened with energy. The May 2024 storm was the first major storm to hit during an era dominated by commercial small satellites, and it exposed just how vulnerable that new infrastructure is. Tractor company John Deere reported that some of its customers relying on GPS for precision farming experienced disruptions during the storm. Farmers using GPS-guided tractors and planters suddenly found their equipment drifting off course. In an industry where accuracy down to the centimeter matters, even brief GPS errors can mean misplanted rows, wasted seed, and lost revenue. Power grid operators around the world went on high alert. The fluctuating magnetic field during the storm induced electrical currents in long-distance power lines. These geomagnetically induced currents are invisible and silent. They flow through the ground and enter the grid through transformer connections. A transformer is designed to handle a specific amount of current flowing in a specific way. When unexpected current from a geomagnetic storm enters the system, the transformer can overheat. Its insulation can break down. In the worst case, a transformer the size of a house can be permanently destroyed in minutes. And here's the problem. Large power transformers take months or even years to manufacture and replace. There are not spares sitting in a warehouse somewhere. If a severe storm takes out dozens of transformers across a continent, millions of people could be without power for weeks or months, not hours. This is not speculation. It has happened before. The last time a GC5 storm hit, in October 2003, it knocked out power in Sweden and damaged transformers in South Africa. And the most famous example of all, the 1989 G5 storm, caused a blackout across the entire province of Quebec in Canada. At 2:44 in the morning on March 13th, the entire Hydro-Quebec power grid collapsed in just 92 seconds. 6 million people lost power. Some did not get it back for 9 hours. Traffic lights went dark in Montreal. Schools and businesses closed. Hospitals switched to backup generators. And that was from a single storm, hitting a grid that was far simpler and smaller than what we rely on today. But here's the truly scary part. You do not even need a big storm to cause big damage, and this next story proves it. On February 3rd, 2022, a SpaceX Falcon 9 rocket lifted off from Cape Canaveral, Florida, carrying 49 brand new Starlink internet satellites. These flat desk-sized spacecraft were released into a low parking orbit about 210 kilometers above Earth. This is standard SpaceX procedure. The satellites are supposed to hang out at this low altitude, run their system checks, unfold their solar panels, and then use onboard thrusters to climb up to their final operational orbit hundreds of kilometers higher. It is a routine that SpaceX had done dozens of times before without any problems. The next day, a geomagnetic storm hit, but it was not a big one, not even close. It was classified as G1, the absolute lowest category on the 5-point scale. G1 storms happen hundreds of times during every solar cycle. Space weather forecasters expected nothing worse than a slight uptick in aurora activity near the poles. A G1 storm is the kind of event that barely gets a footnote in a daily report. But the storm deposited energy into the upper atmosphere. The thermosphere warmed up. And when the thermosphere warms, it expands. The air at 210 kilometers, which is normally extremely thin, suddenly became thicker. Not by a huge amount, but enough. SpaceX engineers later reported that atmospheric drag during the event was up to 50% higher than during any previous Starlink launch. The satellites tried to rotate into an edge-on position to reduce drag, like a knife cutting through the air instead of a flat plate. But it was not enough. The air was too thick. The satellites could not climb. Within 4 days, 38 of those 49 satellites had spiraled downward, re-entered the atmosphere, and burned up. Gone. Millions of dollars in hardware turned to ash by a storm that was barely strong enough to register on the scale. The burning wreckage streaked across the sky as fiery trails, and there was nothing anyone could do to stop it. That event sent shockwaves through the entire satellite industry. If a G1 storm, the weakest possible category, can wipe out a fleet of brand new satellites, what would happen during a G4 or G5 event? What would happen if the magnetic field itself is significantly weaker, letting even more energy penetrate the atmosphere? The answer is that nobody really knows for sure, but the risk is growing with every satellite we put into orbit. There are roughly 10,000 active satellites circling the planet right now, and thousands more are being launched every year. So now we arrive at the biggest question, the one that sits behind every piece of data, every satellite reading, every scientific paper. Is Earth's magnetic field getting ready to flip? Scientists discovered magnetic reversals by studying the ocean floor along the mid-Atlantic ridge, a massive underwater mountain range where new rock is constantly being pushed up from below the surface. As molten rock rises from the mantle and cools, the iron crystals inside it lock into alignment with whatever direction the magnetic field is pointing at that moment. The cooled rock then slowly moves away from the ridge, like a conveyor belt. By measuring the magnetic direction locked into rocks at different distances from the ridge, scientists found a pattern of alternating stripes. Some pointed north, some pointed south. It was a tape recording of every magnetic reversal going back millions of years, preserved in the rock of the ocean floor. That record tells us that, on average, Earth's magnetic poles reverse every 200,000 to 300,000 years over the last 20 million years. The last full reversal happened about 780,000 years ago. By that math alone, we are seriously overdue. Over the last 2.6 million years, the field switched 10 times. But scientists are quick to point out that magnetic reversals are not on a schedule. They are not periodic like clockwork. The processes that drive them, the chaotic churning of liquid iron in the outer core, are inherently unpredictable. Saying we are overdue is like saying a coin that landed heads 5 times in a row is due for tails. It might flip, it might not. Each event is independent. That record tells us that, on average, Earth's magnetic poles reverse every 200,000 to 300,000 years over the last 20 million years. The last full reversal happened about 780,000 years ago. By that math alone, we are seriously overdue. Over the last 2.6 million years, the field switched 10 times. But scientists are quick to point out that magnetic reversals are not on a schedule. They are not periodic like clockwork. The processes that drive them, the chaotic churning of liquid iron in the outer core, are inherently unpredictable. Saying we are overdue is like saying a coin that landed heads 5 times in a row is due for tails. It might flip, it might not. Each event is independent. That record tells us that, on average, Earth's magnetic poles reverse every 200,000 to 300,000 years over the last 20 million years. The last full reversal happened about 780,000 years ago. By that math alone, we are seriously overdue. Over the last 2.6 million years, the field switched 10 times. But scientists are quick to point out that magnetic reversals are not on a schedule. They are not periodic like clockwork. The The processes that drive them, the chaotic churning of liquid iron in the outer core, are inherently unpredictable. Saying we are overdue is like saying a coin that landed heads 5 times in a row is due for tails. It might flip, it might not. Each event is independent. That said, the signs are hard to ignore. The magnetic field has lost about 10% of its strength over the last 150 years. The South Atlantic anomaly is growing and splitting. The North Pole has raced across the Arctic. A geomagnetic jerk began in 2023. Core flow reversed direction. All of these things are consistent with a field in the early stages of reorganization, but none of them guarantee a reversal. The field could weaken and then bounce back. It could wobble and then stabilize, or it could be the opening act of a process that takes another 1,000 years to complete. Professor Chris Finley's team, after analyzing 11 years of swarm data, specifically noted that their study did not find signs of an imminent reversal. But they also noted that the field is clearly in a state of heightened internal variability. The science is honest about what it does and does not know. We can see that the field is changing. We cannot predict exactly what it will do next. If a full reversal does happen, what would it actually look like? It would not be like flipping a light switch. The field would not suddenly snap from north to south overnight. Based on the geological record, a full reversal takes anywhere from 1,000 to 22,000 years. During that transition, the field would weaken significantly. It might drop to 10 or 20% of its current strength or even lower. Instead of having one neat North Pole and one neat South Pole, the field might develop multiple poles scattered across the surface. The magnetic field would become tangled, chaotic, and weak. During that transition period, several things would happen. More cosmic radiation would reach the surface. The ozone layer could thin in unpredictable ways, increasing ultraviolet exposure. Satellite electronics would face much higher radiation doses, potentially shortening the lifespan of every spacecraft in orbit. GPS accuracy could degrade. Radio communications could become unreliable. Power grids, especially long-distance transmission lines, would be more vulnerable to geomagnetically induced currents during solar storms. For most of Earth's history, reversals have not been linked to mass extinctions. Life survived hundreds of them over millions of years. Dinosaurs lived through multiple reversals without disappearing. Fish, birds, and mammals all evolved during periods of magnetic instability. The fossil record does not show any clear connection between reversals and widespread die-offs. But here's the key difference. During all of those previous reversals, humans had not built a civilization that runs entirely on electronics. There were no power grids stretching across continents, no satellites circling the planet, no GPS guiding planes and ships, no internet connecting billions of people, no smartphones in every pocket. Hospitals did not depend on electricity to keep patients alive. Water treatment plants did not need computers to operate. Financial systems did not move trillions of dollars per day through digital networks. Everything we have built in the last 100 years depends on technology that has never been tested against a magnetic pole reversal. We have no idea how well our infrastructure would hold up. Think about what a weakened field would mean for the roughly 10,000 satellites currently in orbit around the planet. Each one of those satellites is a piece of critical infrastructure. Some provide weather forecasting, some carry internet signals to remote areas, some are military reconnaissance platforms. Some keep the global financial system synchronized down to the millisecond. All of them rely on shielding from radiation, and all of them were designed for a magnetic field that was at full strength. A significantly weaker field during a reversal transition could shorten the lifespan of every satellite in orbit. Replacements would need heavier radiation shielding, which means heavier payloads, which means more expensive launches. The cost to the global satellite industry would be staggering. On the ground, the effects would be more subtle, but just as far-reaching. Increased cosmic radiation reaching the surface could affect human health over time, potentially increasing rates of certain cancers and genetic mutations. Airline crews and frequent flyers, who already receive higher radiation doses at cruising altitude, would face even greater exposure. And the ozone layer, which depends partly on the magnetic field to remain intact, could develop new holes in unexpected places, changing patterns of ultraviolet radiation reaching the ground. And that is why scientists are watching so closely. The European Space Agency's SWARM mission is the most important tool we have right now for understanding what is happening to the magnetic field. Launched in November 2013, SWARM consists of 3 identical satellites flying in formation around Earth. They carry extremely sensitive instruments called magnetometers that can measure changes in the magnetic field with incredible precision. These satellites can tell the difference between magnetic signals coming from the core, the crust, the oceans, and the atmosphere. That ability to separate signals is what has allowed scientists to see the changes happening deep inside the planet. On the ground, a network of magnetic observatories spread across every continent continuously monitors the field. These stations have been operating for decades, some for over a century. Together with the SWARM satellites, they give scientists a near real-time picture of how the field is behaving. Every anomaly, every jerk, every fluctuation is recorded and analyzed. NOAA and the British Geological Survey use all of this data to maintain the World Magnetic Model. The latest version, released in December 2024, included something new. For the first time, they published a high-resolution variant called WMMHR 2025, which provides more detailed magnetic data for areas where the field is changing quickly. They also updated the boundaries of the magnetic blackout zones near the poles, regions where compass readings become completely unreliable. As the pole shifts toward Siberia, those blackout zones shift with it, affecting military planning, scientific expeditions, and Arctic shipping routes. The next generation of satellite missions will be critical. Swarm has been operating for over a decade, well beyond its original design life. The 3 satellites are still working, still sending data, still revealing surprises, but they will not last forever. Whatever comes next will need to be even more precise, because the changes in the field are accelerating, and we need finer measurements to keep up. Meanwhile, scientists are also looking at other data sources. A Chinese satellite mission called CSS has been building its own global magnetic field model. Published in early 2026, the second-generation model confirmed the same trends that Swarm has been showing. The South Atlantic anomaly is weakening faster in the east, the global field is becoming more variable, and nonlinear behavior inside the core is becoming more evident, meaning the changes are not following the smooth, predictable patterns that older models assumed. The planet is doing something new, or at least something it has not done since before we had the instruments to watch. So where does all of this leave us? Here's the honest answer. Earth's magnetic field is definitely changing. The data proves that beyond any doubt. The North Pole is moving. The South Atlantic anomaly is growing. The field is weakening in some regions and strengthening in others. Deep inside the core, the dynamics are shifting in ways that surprise even the experts. But scientists also want to be clear about what we do not know. We cannot predict when or if a full reversal will happen. We do not know whether the current changes are the beginning of a reversal, a temporary fluctuation, or something entirely new. The processes driving the geodynamo are among the most complex and chaotic systems in nature. Predicting them is like trying to predict exactly where a specific drop of water will end up in a boiling pot of water. What we can do is prepare. And preparation starts with taking the threat seriously, not as a doomsday scenario, but as a real engineering challenge that the next generation of scientists and engineers will need to solve. Satellite companies can work together to build spacecraft that can handle higher radiation levels. Power grid operators can install protections against geomagnetically induced currents. Navigation systems can be designed with redundancy so that a single magnetic anomaly does not bring everything down. And scientists can keep watching, keep measuring, and keep building better models of what is happening under our feet. Because one thing is certain. The invisible shield that has protected life on this planet for over 4 billion years is not a permanent guarantee. It is a dynamic, living system powered by forces we still do not fully understand. It has weakened before. It has flipped before. It has thrown the entire planet into chaos before. And every piece of data we are collecting right now, from satellites overhead, from observatories on the ground, from ancient tree rings buried in New Zealand mud, is telling us the same thing. The field is changing. The pace is picking up. And whatever happens next inside Earth's molten core will shape the future of every living thing on the surface. We cannot stop it. We cannot control it. We can only watch, measure, and prepare. And right now, that system is telling us something. The question is whether we are listening. If this video made you see Earth a little differently, hit the subscribe button and turn on notifications. We have more stories coming that go deeper into the science hiding beneath the surface of everything around us. And if you want to keep going right now, there's a video on screen about what would actually happen if the sun unleashed a storm powerful enough to fry every circuit on the planet. Trust me, you want to see that one. Click it now.